This is Andrew McGilvery from the Cerberus team at KU, recording a demonstration video for the 2023 IEEE Host Supply Chain Security Competition. So on the right side of my screen here, you can see the layout of our submitted GitHub repository. As the README states, there are two important files in this repository. The first is the one that builds the model, and the second one is the one that runs the model. Now, unfortunately, we did not actually develop our code in this repository. We used a Kaggle workspace with the data set that I can show you right here. And we also did something a little bit atypical. We, instead of just reading out of the folders as they appeared and applying the labels based on the CSV folder or file, we created a subfolder here called phase one workspace with just the phase one data, actually just the phase one training data. And we made a folder with all of the genuine files and all of which are actually authentic, some misnomer, and all of the counterfeit files here. And as I can show you in our code, this makes it a little bit tricky whenever you go to duplicate this. So CNN2 here is the same thing as build model. Let's see, so down here, you'll see all of our paths are set up for this Kaggle workspace. And also we go into that phase one workspace folder, which doesn't exist in the original data set. And we look for the counterfeit and genuine subfolders. So that is why you have all of these files included at the top here. You should only have to change a couple of these paths here in order for this to work and run. Namely, you'd probably need to change the training path here. The training path there, as well as the test path and holdout path. Although this one actually is not used within this file. So to get started here, we define everything for the run at the top. So we have a bunch of the different parameters that we use to train our model. So we have the metrics that we're going to use, the loss function, the optimizer, the batch size, the epochs. Then we have the output filter here. So this is used when we actually run the predictions from our model. It will output a probability for the label instead of a raw 0 or 1. This is the threshold that we require it to have before we apply the 0 label for an authentic IC part. We actually found that that dramatically increases the accuracy even after the training. Down here, the class names, these are pretty straightforward, except note we did use genuine here because of our weird directory structure, but that shouldn't cause any issues. Then we have a few functions. So first we have the find image bounds. This one takes in the image path, reads that image as a grayscale, then it finds all of the rows and columns that have effectively all white space. And then it returns a array identifying those rows and columns. That's used by the trim image function here, which gets those, then it crops the original image based on that. And that's actually used by the process image function here. So it first trims the image, and then we get to work with all of our different feature extraction methods, which are the Laplace and Sobel operators there. So we have this function here just to standardize because this gets called in a couple of different places, notably for the, if we go to the run model file over here, it's important because we have a separate function to load the holdout data, since that does not apply labels the way that it does for the load data function. So we just have this standardized right here so that we know that we're actually processing the input images the same way for training and prediction. So once we move on from there, there's that load data function. this cell loads in all the images. Now, note that we did specify a few to skip because we figured that they were kind of contradictory to the label that they had. We didn't think that they were good examples of either a counterfeit or a authentic part. Then we pinned all those into a NumPy array that we can use as the input to our model. So once we have that training data right there, we go ahead and we get the test data as well, because we do test the whole model at the bottom of this file. The model itself is built right here with code that Faith actually wrote. Then we build the model with the inputs that have the shape we declared right here. So it's just the image size, and then there's 3 dimensions RGB. And then we find the output right there based on this line here. We compile this with the metrics, loss, and optimizer values that we specified at the top of the file, and then we get the summary of this here. Then we do the actual training data in this cell. So what we found was that the validation loss really spikes if you do too many epochs of training. And also the accuracy for the validation set doesn't really go up either. So you're not really gaining much. So we stopped it fairly early at around 20 epochs. I believe that's what we use to get the model that we actually provide. And once we get it out, we pretty print the history here, all the metrics, and then we go ahead and we start to test. So if you remember up above, we actually exclude some of these bad cases from our training data. So first we add those back in. So we reread all of the files and make sure that everything's in there. Then we go ahead and we call that predict with confidence known vals from the top of the file. I can pull that up on the right side of the screen here. So this will just run the predictions and then print out some statistics. So here for the model that was trained last time I opened this file, you can see that it got 75 predictions correct out of 100, which is pretty decent. And then for the validation set, where you would expect some lower accuracy here, we do see lower accuracy, so 75 to 65%. So the model might not be the best fit. It might be too specific to the training data. But that is not from the run that we are submitting. To actually run the model, remember the other important file, as we mentioned in the README, is run model, which is shown here on the left side of the screen in the Kaggle environment that we have. So this here, it looks like there is a slight error here, so this should actually be 0.15. Let me go ahead and we'll edit this and run it and show it loading and running the model that we are submitting. Actually, it looks like it did get fixed. I'm not sure why that was wrong there. So this starts off basically the same, but we define the extra load predict method here, which just is specialized to not append labels. And so it just appends the image paths so that we can print a nice output at the bottom of the file. So see here, we print the sample alongside its prediction. So if we go ahead and run this, let's double check everything's correct. So we have, again, all these paths. So if you fix these in the build model notebook, you will also need to fix them here. You could also just exclude the cells that run on the training data if you don't want to have to copy this whole GitHub repository. But if we run it in this Kaggle environment, so we've got just one more check. Yeah, T75, or sorry, T77V75, that's for training, 77% accuracy, validation, 75% accuracy. So we can go ahead and start to run this. Everything looks correct. And I do know that the run model in the GitHub repository itself, I triple checked that before we put it in the submission. So this is correct from here. It's just the Kaggle environment is a little bit wonky. Which is why I was concerned there. So let's see. So first it's reading all of the directories to get the training and test and holdout data. And this might take a moment. Go. Okay. So let's go back and look at what that did. So for the actual holdout data, it does go ahead and write the let's see, I clear, oh, here we go. It does go ahead and write out the processed input like sample files here. So if I save this, let's go to this folder here. I can actually see what went into the model for sample 5. So this is the output from our Laplacian and Sobel filters. Then we have this where it runs the model for the training set, and it gives us that confusion matrix. We see that we have the 77% accuracy. Then we run on the test set, we get 75% accuracy, and here we finally run on the holdout set, and it gives us all of these predictions for the samples that match what we have in the sample submission.csv right here. And do note sampleton is printed out of order in this file. I believe that's everything. Thank you so much. And yeah.